Okay, so welcome to the 31st video in the Discrete Structures series, and we have been covering the chapter of induction and recursion. And under induction, in the last two videos, we have covered the concepts of mathematical induction and strong mathematical induction. So today we'll be looking at the last topic inside of induction, and that is going to be the well ordering property. So we have done a little bit of discussion already on the well ordering property when we were discussing our topic of mathematical induction and why induction works. So today we'll just be revisiting those concepts in a little bit of detail, and we'll be solving some problems under the well ordering property. Alright, so let's get started by looking into the introduction to the well ordering property. So this should be a relatively quick discussion because this has a very simple statement. Every non-empty set of positive numbers has a list element. So if I consider the set of natural numbers, for example, we can see that this has a list element of 1. And I could have any arbitrary set with positive numbers. And as long as we can ensure that this set is non-empty and it only has positive numbers, we can guarantee that it has a list element. And for this set, we see that the list element is 23. And I have also mentioned this earlier, this does sound like a really obvious thing to say, but we should appreciate it because it mentions the set of positive numbers. If we are looking at a potentially infinite set where all numbers are not guaranteed to be positive, we cannot guarantee a list element. For example, consider this other set R with all negative numbers -1, -2 and so on. It goes up to infinity. And this set R does not have a list element because for negative numbers, increasing magnitude makes the number even more smaller. And the reason this property is so important is because the proof for mathematical induction follows from the well ordering property. And it is an absolutely established fact on the mathematical world that the well ordering property, the mathematical induction, and the strong induction are all equivalent to each other. And in fact, I don't want to claim that I have given a formal proof, but in our last two videos, we have already seen why the well ordering property implies the mathematical induction process. And in our previous video about strong induction, we also looked at how strong induction just followed from the reasoning process of mathematical induction. Now, in order to complete this equivalence proof, we also need to show one more implication, that the strong induction proves the well ordering property. But we'll not be covering that as this equivalence is not the part of our course, but it will absolutely help you to know that all of these three proof techniques are the same. So the goal of this video is going to be about building a better idea for the well ordering property, and we'll do that by solving some problems. And in fact, let us get into those problems now. So I prepared two main types of questions for the well ordering property, and we'll solve those questions here. So getting into the first question, let me write the question down. Given a round robin tournament, every player plays against every other player exactly once and there's always a winner. Given that there exists a cycle of m players and m is given greater than or equal to 3, prove that there must exist a cycle of exactly 3 players. Alright, let's try to understand what this problem says. We'll first try to convince ourselves that we understand this problem and understand that there will be a cycle of exactly 3 players. So I'll do that demonstration using a diagram here, and then we'll do the formal proof on this side. So what is the question saying? It is talking about a round robin tournament. A round robin tournament is a tournament where there could be any number of players. So let's say there are n players total. And the idea is everybody plays against everybody exactly once. So a 3-player round robin tournament will have 3 total games, and a 10-player round robin tournament will have 45 total games. So the count 45 comes from the fact that this is 10 choose 2, or the combination of 10 things taken 2 at a time. Because we have 10 total players and each game is played by 2 people. So the number of ways we can choose 2 people from a group of 10 is the number of games that will happen. And that will be equal to 45, but that is not relevant to the discussion of our video. Next, let us understand what a cycle is. So if player 1 wins over player 2 and player 2 wins over player 3 and 3 also wins over 1, we have formed a cycle. Okay, 1 beats 2, 2 beats 3, 3 beats 1. And what is the length of this cycle? The length of this cycle is 3 because there are 3 players that make this cycle. You should understand that there could be larger cycles. 1 could beat 2, 2 could beat 7, 7 could beat 9, 9 could beat 13, and 13 could finally beat 1. And this is a cycle of length 5. And I can imagine these cycles in any way I like because this is a round robin tournament. Everybody is playing against everybody. So what is the question saying? The question says that if there exists a cycle of m players and m is greater than or equal to 3. So it could be a cycle just like this with 5 members. And the question asks me to prove that if this cycle exists, there also exists another cycle with exactly 3 players. So I can mention it strongly by stating that if any cycle exists at all, a cycle of 3 players also is guaranteed to exist. Now let me show you why this cycle of exactly 5 people is enough to guarantee another cycle of exactly 3 people. So let me clear a little bit of area here. I'll draw a slightly bigger diagram and demonstrate. So the question has given me that there is one cycle of at least 3 players. Okay, so I'll just draw a big circle, and this circle could have any number of people more than 3 and the proof would still be true. But for demo purposes, I'll say this cycle has 5 people. And let's say these people are A, B, C, D and E. Now the question has given me that a cycle exists. So let us assume that A beats B and then B beats C, C beats D and so on, and finally the cycle completes with E beating A. Okay, so this is a complete cycle. It was a round robin tournament. Everybody played with everybody and A wins over B and B wins over C and so on. It loops to a cycle of 5 people. And this is exactly what the question is saying. It has not mentioned 5 people. I chose 5 on my own for demonstration, but it actually works for any number greater than or equal to 3. Okay, so let us see how we can guarantee a cycle of 3 people here. So from this diagram, I can guarantee that A has played against B and won. B has played against C and won. And because this was a round robin tournament, I can guarantee that a game between A and C also happened. Now this game between A and C could have two possibilities. Either A could have won or C could have won. And if C won, I can say that C wins over A wins over B and B wins over C, and my cycle is complete. I hope you can see that if C wins, the cycle is complete this way. Now listen to this carefully. Our main argument when C loses, that is if A wins over C, B is not needed in my cycle, and then I'll repeat the same process with A, C and D. Because now from this structure I can say that A has beaten C, C has beaten D. What happened between D and A? And can you see how this process will eventually guarantee a cycle? At this point, A has beaten C, C has beaten D. Now if D beats A, my cycle of 3 people is already complete. But if A beats D, then by the same logic C was not needed in my proof. And then I'll continue looking in exactly the same way. I'll look at A, D and then E. And then if I ask the same question, A has beaten D, D has beaten E, what happened between A and D? And geometrically speaking, this circle is gonna run out of chords. So if I keep denying every chain of 3, the last chain will be the chain of 3 that I'm looking for. So A has beaten D, D has beaten E and E has beaten A. Okay, please make sure that you understand the reasoning process behind this, and now I'll show you what the solution looks like using well ordering property. So we'll prove this statement by contradictions. We'll first assume that there is no cycle of exactly 3 players, and we'll eventually show that that cannot happen. So let's begin doing that. So second, we consider the sets of all cycle lengths. We are not looking at the process of generating the cycles, but we are abstractly saying to collect all the cycles in a set. So this set is going to have my main cycle A, B, C, D, E. It's going to have the sub cycle A, D, E. It's going to have the sub cycle A, C, D, E. Okay, so all of the possible cycles are in this set. Okay, the next thing that I'll do is to claim that this set is non-empty, because I'm given that there is at least one cycle of M players. This is given by the question. So that cycle will be inside this set of cycles. So I can guarantee this will be non-empty. Then we can claim using the well ordering property that this set has a least element. Does this complete the proof? Obviously not, because I still need to prove that this cycle of least element has exactly 3 players. And I do not know that yet. So I'll assume that this element is a K cycle. So all we are saying here is if the cycle that the question gave us, the cycle with M players, is the only possible cycle in the entire thing, that will be my only cycle. Now if there are other cycles, I can at least guarantee that the cycle length is at least 3. Because if there exists a cycle of length 3, I don't need to prove anything. So we'll just assume that there is no cycle of length 3. We'll consider the set of all cycles, and we'll say that by the well ordering property, this set of all cycles does have a smallest cycle. But we don't know that the smallest cycle contains exactly 3 elements, and that is what we need to show. And since we don't know 3, we just say K. So we assume that the smallest cycle has K players, where K is greater than 3 and less than M. Now we want to be able to show our contradiction by saying that K is not the least element, because we know that the least cycle is 3. So we'll use the argument that we had here in order to derive a cycle length that is less than K. And if we are able to do that, it means that there exists a shorter cycle, and that would apply for any K that is greater than 3. Therefore, the shortest cycle must have 3 elements. But that is the main challenge. How do we show that there exists a shorter cycle with less than K players? Okay, so let us get a little bit of space. I hope it doesn't matter too much that the question is covered. Alright, our next logical reasoning step is gonna say the following. Now since my assumed cycle of k players has at least 3 members, I will take the first 3 players in this cycle. I'll take the players P1, P2 and P3. And here you should try to correlate it to the discussion that we had earlier. It is just like choosing A, B and C, the first 3 players. And what was our logic? P1 beats P2, P2 beats P3. That is given by the question because this is a cycle, right? P1, P2, P3 are part of this K cycle. Therefore, P1 beats P2, P2 beats P3. You can see here A beats B, B beats C. So in the next step, we consider the match between P1 and P3. Now we can argue that if P3 beats P1, the cycle is already complete. And in the other case, if P1 beats P3, this is not my shortest cycle because I could form a shorter cycle by skipping P2. And this is a contradiction because we can say that P1, P3 and so on is a shorter cycle. Because my original assumption was that this path from A to B, B to C, C to D, D to E and E to A was my shortest cycle. But if A beats C, I do not need B. So A, C, D, E is another shorter cycle than that. So this proves that anytime my shortest cycle has more than 3 elements, I can always find a shorter cycle. And therefore the shortest cycle is guaranteed to have exactly 3 players. So this should be the most important question on Wheel ordering property in my personal opinion. But there is another question that I have. I'll show you that question. So this question says prove the division algorithm using the Wheel ordering property. So the division algorithm is something that we have already taken care of in our earlier chapter of integers and matrices. And there we talked about the fact that the division algorithm is not actually an algorithm but a theorem. And this stated the basic property of division. When I divide any number A with any divisor D, I am bound to get a quotient Q and a remainder R. And let's quickly bring this into context. When I was doing 24 divided by 5, we would find the quotient and remainder by writing an expression like this. 24 is equals to 5 times 4 plus 4. And in this expression, this is my number A, this is my divisor D, this is my quotient Q, and this is my remainder R. So the division algorithm is basically a claim that if you are given any number A, and A could be any number positive or negative, and this divisor is assumed to be a positive integer. And if that is the case, I can always find a unique quotient and remainder such that A is equals to D times Q plus R. Okay, so given A and D, Q and R exist. And we also established that if I'm dividing by a 5, the remainder can only be 0 to 4. So my remainder here should be in the range of the divisor. So 0 less than or equal to R less than D. So rephrasing the division algorithm again, given any number A and a divisor D, we can always find a quotient Q and a remainder R so that the remainder is less than the divisor. And the 0 is here to signify that the remainder is positive. We can guarantee a positive remainder. Now the Wheel ordering property is only useful for half of this proof process. The first part of the proof will show that Q and R exist, and we'll do that using the Wheel ordering property. And the second part of the proof shows that the quotient and the remainders are unique. So a given division operation can only produce one quotient and one remainder. And you should recall the pattern that we always use in our Wheel ordering property proofs. We first start by considering a set, and then we consider the least element in that set and do something with it. So the first step in the proof of this problem is to form a set of all possible remainders. And this is equivalent to the set of A minus DQ for every integer Q. And why is this? Technically, I could just show you this expression because R is just equal to A minus DQ, and that is a generalized remainder for any integer Q. And you should also understand that when I'm constructing this set A, I'm ignoring this constraint. Because if I want a remainder between 0 and D, I do not have many possibilities. There's just going to be one remainder between 0 and D. And this set is just going to have one element. So in order to use the Wheel ordering property, we are just considering all possible values of A minus DQ. But we know that this set of all possible remainders will have a least element, and that least element is bound to be between 0 and D. Okay, our first argument is to mention that this set is non-empty. That is necessary. And why can I guarantee that this set is non-empty? Because I'm choosing from the set of integers. Integer can be negative, so I could choose my quotient to be anything negative and a sufficiently large number so that A minus DQ is always positive. So let's say A is a million. I'll choose Q as minus 10 million, and that minus and this minus will become a plus, and it will be a sufficiently positive numbers. So since Q can be chosen from the set of integers, I can ensure that there are infinite positive numbers in this set. And I am ensuring to only collect the positive numbers and ignore all the negative numbers. So they are not in my set. And since this set is non-empty and it only has positive numbers, we can guarantee it has a least element. We call that least element R, and we can say that is equals to A minus DQ. And doing this, I have found my R. But looking into it numerically makes it easier. Let's say I am dividing 24 divided by 5. All this set is asking me to do is start my collection from 24 and include all the positive remainders. So I could do 24, that is also a remainder. When I do 5 times 0, 24 remains. You should be able to see another remainder is 19 because 5 times 1 is 5 and that leaves 19 for a remainder. So the set is just asking me to take 24 and then keep subtracting the multiples of the divisor. Another remainder, when I take the quotient as 3, 5 times 3 is 15 and then I get a 14 for a remainder. So I'll just get 9 and 4. And the well ordering property is saying that this set has a least element and that is my remainder. So we first take all possible values for the quotient q and that gives us all possible values of the remainder. And the least value is the remainder that I'm looking for and the quotient corresponding to it is the quotient that I'm looking for. Therefore, I've proven that both q and r exist. Alright, that completes the discussion for today's video and the first part of induction in our chapter of induction and recursion. We'll start next video with a look into recursion and recursive algorithms. So I'll see you guys tomorrow on the next one. Have a good day and bye.